Exactly. So we start for the second lecture. It's a little less full of colorful pictures since yesterday, as compared to yesterday. So I just called it like it's the manual because there is a lot of techniques which are in there which you might find useful for analyzing then multiplayer evolutionary games. We will come to the homework thing if anyone has ever like given it a thought. So, but we will come to it at some point, and I would appreciate some feedback if you have at that point. But not right away, right? So, okay, so this is what we actually did yesterday. We had some kind of a very general introduction to multiplayer evolutionary games, and then we explored this interesting connection that it might have to population genetics, at least in that one particular way. Today, we are going to be, I have to stand like this. Yeah, that was supposed to come. All right, that's what we did yesterday, trying to understand what happens when you add a new strategy. Not so much, except making things bigger. Adding a new player, making things explode in dimensions a bit more. Then how to write it down by compactifying it a bit so that it's a bit more amenable to our methods. Not that it's a problem, but still much nicer to look at and easier to interpret, actually, in a way. And then we explored this connection, right, to population genetics. I really need to stand this side. And then I guess I need to point it towards right, so, but in the second lecture now, today, we will actually try to see how we can analyze such kind of games, right? So I just call it if, when, how, and what I mean by all of these things is how. So actually, how do we actually see the dynamics? How do we move from a static to a dynamic environment? I also put a why question because that's one of the leading questions which you should kind of include usually, but I did not put it in there. If we have time, I will address the whys of it. But for now, it's actually just how. The if is all about probabilities. Do we actually see things happening the way we want them? For example, the probability of fixation and then the further properties that follow from it. When, the question about time. So then we will ask something about the fixation time of such a process. So we are basically going to be moving from deterministic systems then to stochastic systems over here, where in the final case, we will also analyze the mutation selection equilibrium. So what happens when you do have mutations in selection, both going on in your process, and how do you look at the long-term dynamics of such a system? I guess you might have seen all of this for two-player games or not, but we will, okay, this is still taking time. Okay, that's where we will try to start. Move it a bit. Hopefully the connection works. So let's start with the how questions, right? As I said before, a lot of theory exists for two-player games with two strategies. And you might remember some of this from the whole last week, from yesterday or something. So we will just reiterate a little bit of that, and then we will try to see how we can extend it, right? But just to get us all on the same page again, I hope you remembered the intuition behind the notation over here. So the subscripts, again, in the pair of entries, they just tell you how many of the other A players you are playing with, right? And A is then the payoff for the A strategy and B is for the B strategy. Things might change a bit further on, but that's more or less the generic idea of writing these payoff entries in that specific manner. With that, actually, you can immediately come to the concept of an evolutionarily stable strategy. And in this case, thinking about A being an evolutionarily stable strategy, what is required then? Well, then A should be able to repel an infinitesimally small amount of B individuals who try to invade in the population, right? That's what you want. And you can have two different definitions of this ESS, then making it very strict, saying that A1 should be larger than B1. So if everyone is at A, there should be no B trying to invade it, right? But there could be also slightly a weaker definition which says that, okay, maybe B can slightly invade it because A1 equals B1, but B will never replace A. And that would be because A0 is greater than B0. And this actually connects it to the other points of the Nash equilibrium which Sagar asked yesterday. And so I put this slide especially for him. I think I will change the clicker, okay? Because this is not best. It doesn't let me move around as freely as well. Let's see if this works, or was it just me, actually? Yeah, that works. So this is the slide I actually put in for Sagar. So this was a report that Carl Zygmunt wrote for the IISER, and where he did mention that John Maynard Smith was not familiar with the vast literature on Nash equilibrium selection, which already existed in Peter Hammerstein, then a PhD student who was at that time together with John Maynard Smith and Reinhard Selten, actually put it right. And Maynard Smith actually mentions that in the preface to his book. But the interesting thing is, nevertheless, he unabashedly kept confusing the concept of an ESS with that more general of a Nash equilibrium, or with that more special of an unbeatable strategy, which had been defined, although implicitly, by Will Hamilton. So until the end, he was like just going back and forth between the two a bit. So that might explain some of the confusions that you might see in the literature, right, sometimes. But given that, you can actually classify those things, right? So you can go all the way from just a Nash equilibrium, which might be a very loose concept, all the way to a strict Nash, and in between you encounter then a weak ESS, ESS concepts, right? So you can have a classification on them just by looking at your payoff matrix. Is a strategy that you're interested in this case, again, we are talking about A, is at Nash, or is it just a weak ESS, ESS, or a strict Nash, right? If things are not clear, please interrupt me again, right? Because all of this was, you know this very well, we have been listening about this. And the thing was, this was a static description, right? And I really liked what we heard today morning as well, when the focus was very much on like, okay, you do have this equilibrium dynamics, but the question was like, how do you reach it, right? And something really interesting can happen on the way. So the temporal dynamics is kind of quite interesting many times. And Morgenstern and von Neumann also recognize that already very presciently, that we repeat most emphatically that our theory is thoroughly static. A dynamic theory would unquestionably be more complete and therefore preferable. They were really pushing for that at that time, and thankfully we are going to be using replicator dynamics, which again you have been hearing a lot. I know this is a lot of repetition. Bear with me, we might use some of this, right? It's just putting things back in a certain notation which we will be able to use again. That's the only reason for that. So in this case, then what we are interested in is in the change in the number of A individuals, right? A players over time. That's what we want. The frequency of A players, you just set it to X, and then what we are interested in is the payoff of A players, and in this case, pi A, which is then you just multiply pi A with X, A1 with X, and A0 with 1 minus X, right? Because those are the proportions with which you will encounter A and B players. In this case particularly, we say that payoff is fitness, and with that you can then write down the replicator equation for the two types, which is simply X1 minus X, and then fitness of A minus fitness of B, right? And this is something that we already saw, that you can write down the dynamics in this simplex, but the one way of writing it down would be on the x-axis, you have your simplex, 0 to 1, but on the y-axis, you can just plot the replicator equation then, which will tell you what kind of dynamics you expect to see in this system. And for this particular generic two-player game with two strategies, do you remember the 4 kinds of dynamics that you are expected to see? Anyone? No? There are 4 kinds of dynamical outcomes, right? Which you would see from this equation, depending on the payoff entries, of course, and that would be dominance. So either one type is dominant over the other type. You get some kind of coexistence, right? Where both, well, the dynamics from both of the sides lead to some kind of interior equilibrium point. But you could also have bistability, where from that interior point, actually you move away. It's an unstable equilibrium point. And if you have no difference basically in the fitnesses, if the fitnesses are exactly the same, it's a line of fixed points. You just stay where you are in that case, right? Those are the 4 dynamical outcomes that you would see. A cool thing which I wanted to mention yesterday, but since we were not talking about dynamics yesterday, is that this kind of relationship, actually you can transform it again to something in genetics. And this was done actually by Ross Cressman using a slightly different methodology than from what we discussed yesterday. But in essence, what you can do is you can actually map a dominance game to a dominant genetic mapping, so where exactly one genotype is more dominant over the heterozygote over the other homozygote. Or you can model over-dominance, under-dominance strategies, or even neutrality. Right? So there is a very nice connection actually also in this space, in the dynamical space, right?
So is neutrality sort of co-dominance?
No, that would be something with underdominance, right? Where they're both, or I would not know that term, how it's defined actually. Wouldn't that be overdominance? So like somewhere in between. What, what is that again? Okay. Which would be the heterozygote phenotype, right? Exactly. No, exactly. Yeah, this is purely at the phenotypic level, right? You can track it at the phenotypic level. Yeah. Yeah. I have the same, yeah, and then you see that in the bit, and you only see the heterozygote because it's discrete traits, and then you will get the heterozygote, right? Okay, thanks. There you go. Right. So, but then how do we calculate this interior fixed point? Exactly, that's what you're talking about. And then you just equate the fitnesses, right? FA is equal to FB because that was the interior fixed point. The trivial fixed points were given by your x and 1 minus x of being 0 and 1. And the interior fixed point is just where the fitnesses are the same, right? And this is the expression that you get for the equilibrium point in the interior. Now this may or may not lie within that simplex. So if it does lie, then you do get the interior fixed point, and then it might be stable or unstable, giving you the dynamics that we saw earlier on the slide. Is this fine still? This is just a recap, right? You guys know this stuff, hopefully by now. If not, we are in trouble. But if you do, things should be fine. If not, please let me know, right? I'll go, that's why I'm going a little bit faster over this part, right? Because then we can slow down actually later. Because this is basically the summary of these 2x2 games that we do know of, right? In the deterministic case, we have this dynamics which goes on this simplex, right? For a two-player game with two strategies. It's because it's two strategies, you can still represent by this single line, right? That's the simplex that we're interested in. The dynamics, which are possible dynamics that you can see, there are these four possible dynamical scenarios. That's also fine. You have dominance, you have one interior fixed point, stable, unstable, or you have a line of interior fixed points. Okay, that's still fine. If that's fine, then you can start looking at a stochastic system and start asking questions about the probabilities. Big push to this field was given. I mean, people had been working on finite populations for a very long time, but within evolutionary game theory, at least, a very big push was given to the understanding of stochastic dynamics after the publication of this paper, which was on the emergence of cooperation in finite populations. And they, not just showing the importance of it, they actually developed a lot of theory, actually already within it, right? Which you might find useful now because we will go through it a bit. And one of the processes which you can use many processes, right? Which at the stochastic level to actually model the population dynamics. A nice one to use is the Moran process, where you have a population at a certain state, given over here on the left, made up of these two types, A and B. Yeah? And in one time step, either of those three things can happen, right? You can increase the number of, say, in this case, A individuals by 1, you can decrease it by 1, or you can stay the same. And the probabilities with which that can happen are given over here, where you basically choose an A player proportional to its fitness. So that's the first fraction, right? You choose it proportional to its fitness, and then you choose a B individual to die. And that would increase the number of A individuals by 1, right? You can decrease the number of A individuals in the opposite manner, where you are actually choosing a B individual to reproduce and an A individual to die, right? So if we didn't have the fitnesses over here, this would just be a process in which you flip back and forth. That would be a random draw of your dice. But because we have the fitness actually loads the dice, because in a certain manner, maybe the fitnesses are different, right, as we saw. And because of that, your transition probabilities are not perfectly balanced. If they were perfectly balanced, we actually get rid of the deterministic description, we move along this line, and in case of the transition probabilities to increase or decrease to be exactly the same, you can actually calculate the probability that if you do start with a single individual of a blue type, let's say, the probability that it will reach fixation, the probability that at some point later in time, the whole population will be blue, is then simply 1 over n, right? You can start with any number of blue individuals, the probability will be that fraction over n, right? So I over n, basically. But in this case, we are mostly interested if you start with a single blue individual. So that would be just 1 over n. For the stochastic processes, usually you try to also use a different payoff to fitness mapping. And there are various reasons actually why you would do that, because the argument can range from, okay, game doesn't really have that much of an impact on your fitness. So there are other things that matter, and this game contributes a little bit to this fitness. And that's why you can actually think that there's this omega, or usually omega or beta, something that people use. It kind of tunes the impact of that game on your fitness. Another way of looking at it is like you might be playing several different games, right? And each game contributes only a little bit to this fitness. Maybe some games contribute more, some games contribute less, and you can tune the impact of those games onto your fitness by some parameter. And that's what this argument for usually is. Next, the argument is that it's good for your mathematical convenience. But yeah, that's something that's just falls out, right? Totally not planned. So now we do have this omega which tunes the impact of the game on the fitness, and with that we can actually do some things, right? Because we can calculate the fixation probability. The probability that you actually will take over the population will be, in the case of neutrality, 1 over n, right? Plus there will be a correction because of this, a little bit of weak selection that we will impose. We will have a correction on top of that, right? And this correction takes this form, but the nice thing about this form is it just consists of the difference in the payoffs, actually, right? Well, I mean, you're summing it over the population size, but in principle, what you're summing over are these differences in the payoffs. And we know the payoff matrix very well. So all we need to do is, this object over here, we need to ask if that is larger than 0. Because if that is larger than 0, the term on the right-hand side over here will be positive. That means the fixation probability will be more than neutral. It will be more than just by chance, because by chance the fixation probability is just 1 over n, right? So if the strategy is selected for, a signature for that would be that the fixation probability is larger than just by chance. Is it fine? Is everyone with me? Or yep. Sorry, could you? Yes, so there is actually a different study that we did do on which is about how small should be the selection intensity. So you can put some norms on it, like how large is large, how small is small, and then you can actually calculate some stuff. Usually we did see that 1 over n squared usually fine for omega. It's similar. Well, I mean, if it's very large, you don't need all of this, right? Because then you're doing infinitely large populations. Yeah. Because then things will get problematic anyways, because then you're not calculating fixation probability. Yeah. Because then this is a large term. So we have this very nice argument that the fixation probability will be larger than neutrality, will be larger than 1 over n, if this gamma is larger than 0, right? So we just need to look how this gamma looks like in a bit more detail. And if you just simplify it a bit, these double summations, it comes out to look like this, right? You have some properties of the n in it because you are summing over them, but mostly you are just dealing with the entries of your payoff matrix, which you do know. You can do a second approximation now. You can say that, okay, we are looking at finite populations, but let's say we are looking at some large finite populations, right? So the n is large enough, but not too large, because otherwise it would be infinite. So you stick with finite populations, but a large n. And if you do this kind of analysis, right, if you say that, okay, now we're still dealing with finite populations, but large populations for weak selection, which was still in there, we have that the fixation probability is larger than 1 over n if this particular inequality is true, right? So again, now you're looking only at the payoff entries. So the thing is, if you do know what your payoff matrix looks like, which comes from a deterministic case that you have exactly the payoff entries, you can say something about the fixation probability in finite populations just by looking at those entries, right? And the cool thing about this is, the reason I've put this over here is that it shouldn't have appeared right now, it should have appeared now, is that this corresponds to something which is known as the 1/3 rule, right? Because the thing is, we did not impose any kind of constraints actually on the entries of the payoff matrix. So this should be valid even for a game which looks like this, which has an unstable equilibrium in the interior. And if you rearrange this inequality, what it gives you is B0 minus A0 over A1 minus A0 minus B1 plus B0 less than 1/3. But the thing is, we know what this left-hand side looks, what does it mean, right? We just solved it a few slides ago. That was the interior equilibrium. So what this says is that the interior equilibrium is, if it is less than 1/3, then the fixation probability is still larger than 1 over n, especially in a game where that interior fixed point exists, right? So the deterministic dynamics is going to push you towards extinction, but in the stochastic sense, in the stochastic dynamics, you will have a fixation probability which is actually larger than 1 over n. Right? Is that, yep. So you move things around a bit and then feel free to try it out. If it doesn't, yeah, let me know. Right, so it's basically rearranging these terms. Yeah. Sure. I would go through the whole derivation, but those actually come because you have to take the ratio of the transition probabilities, and the transition probabilities you can also go up and you can also go down. And you have to go through from each state where you are, where do you do, what do you do, right? Exactly. Yeah. Exactly. So the idea is you are at each state in this chain, right? And you want to know that from each state in this chain, the probability of going up and down will be. So it is in the ratio of the transition probabilities, which you don't see anymore. And that's because once you take the ratio of the transition probabilities in context with weak selection, so the ratio of the transition probabilities would actually end up being 1 minus omega plus omega times FB divided by 1 minus omega plus omega times FA. If you take the ratio of this ratio, but in the limit of omega going to 0, right? And because of that, then you are just dealing with the difference between the payoffs. And then the ratio of them becomes the difference, rather, because of the double summation. I can go through the whole proof actually together with you if you want. Yeah, we can. Yeah, but then you do that at each step, and then you sum over all possible m's then as well. Yeah. Right. So the argument over here is that even though we are looking at a stochastic system, information from the we can say something even about the deterministic system, because this is just a bistability region, right, which we were talking about in the deterministic system. But we can make a comment about that, how it will behave as a stochastic system, how the fixation probabilities will look like by just knowing this inequality over here. But the thing is, it's a system which is moving in time. So you are moving from here to here to here to here to here and finally to n, right? So at some point in time, I could ask the question again when there are only n minus 1 blue players and 1 red player, right? I can ask the same question again. What's the fixation probability of this 1 red player in this population? Because I want to calculate that reciprocally, and so what is of interest is the ratio between those fixation probabilities. So which fixation probability is larger? Fixation probability of A or that of B? So we can take a ratio of those fixation probabilities again and ask the question, okay, how does this ratio look like? And now here again, you see a ratio of the transition probabilities again, but now they appear as a product. I can again tell you why, but we have to go through that again. This is more involved than the calculating the fixation probability itself, because actually sometimes the probability appears in it. But this should be an omega. So that's again for weak selection. But what you end up seeing is, again, what you're interested in is the difference in the payoffs. So we will actually say that the difference in the payoffs is the thing that determines what fixation probability, which fixation probability is actually larger than the other. Because in this case, all you need to know is if this phi is larger than 0, right? So for finite populations then, the phi larger than 0 looks something like this, right? So if this is what it looks like, we can again use the same trick as before. We can say that, okay, the population sizes are large enough so that we can do some approximation on this n. And if we do that, actually what we get is just simply A1 plus A0 larger than B1 plus B0, which is also known as then the condition for risk dominance, right? So which strategy is basically risk dominant in these finite populations where it's easier to move towards the left or towards the right. So take over basically probabilities, which one is larger given just by the sum of the payoffs that your strategy gets. So again, by looking just at the payoff matrix, you can tell these two things, the 1/3 rule and also which strategy is going to be risk dominance just by looking at the entries of the payoff matrix. So you don't worry about the -2. You don't worry about the -2. So it's large enough than 2 to make sure it's fine, things are fine. And then it's not too bad an assumption, I would say. So So this is the summary then for the 2-player games with 2 strategies, the deterministic dynamics and the stochastic dynamics for these 2 conditions. And exactly that's what we will ask now. How does it look like for multiplayer games, right? Yes, please. Could you speak a bit louder, please? Again, I would need to go through the whole derivation for that, and I'm happy to. But there are some actually intuitive arguments for that. Like how often do you actually, like at what rate do you need to overcome meeting your own strategy versus how often do you need to beat the other strategy when they are rare? So that's actually the argument. That's a good question. So you see, the importance thing is at this point, right? B0 when the other strategy is rare. That's the payoff they will get when they as B0, because then there will be mostly no A individuals, and for the A individuals to invade at that point, that part is important. Whereas what is also important is that when they are already in the population, they should not be invaded again. So there are these arguments actually why there are some discrepancies between the payoffs which you see at the extremes. When A plays with A or B plays with no A almost, so very few A. So because at that point they need to invade, and at one point they need to maintain. So there are these intuitive arguments actually for why you do see this asymmetry actually. And you will see this again popping up, hopefully. So because now you have the summary for these, and the question which we ask is, okay, can we say something about multiplayer games, right, with this? Like how much of this carries over, exactly what Supratim was asking. So let's take it again slow. Let's look at the deterministic dynamics, right? Let's build it up. Because this is the space that we want to explore, and we want to increase the number of players now, right? Just like we did yesterday. But again, we are still starting simple. So instead of any number of players, let's just start with a three-player game, right? 2 strategies, but 3-player game. At this point, we come to the exercise, which we had discussed yesterday. Did anyone bother looking at it? I'm totally fine if you did not, because it's very hard to do. I mean, it's an intense school, so yes. Okay, but maybe we can walk through this then if you want. So if you do have this kind of a game, what do we want to do first of all, right? The very first thing that we want to do from this is we want to understand the average payoffs, exactly, the average payoffs of those strategies, right? And since we only have two strategies, things are, first of all, good for us because we are trying to understand deterministic dynamics, but what we at least know is that the dynamics is still going to happen only on this like one-dimensional simplex, right? Things are easy in that case. One is blue, one is red, and that's it. What we want to find out, though, is what the fitness looks like of the two strategies. So the fitness of the blue, so I'm assuming fitness of the blue is equal to so the payoff is the same as the fitness, and that's what we want to calculate, right now. It's a three-player game. I will meet these two guys, which are both blue, right? And if the frequency of the blue individuals is x, then I'll need to meet two of them. And I will meet the two of them with the probability x squared, one after the other or something. And when I do, then I will get p over 2 minus c, right? Or I will meet one blue or one red. I will get b minus c. But then we have this problem of combinatorics, right? Because the first one could be blue, second red, or the first could be red and the second blue. So we have to multiply this by 2. And the last term, which is you get minus c with probability 1 minus x squared, right? Is this fine? Okay. Well, okay, yeah, I tried to write it more generically because I had already typeset AK and BK. So that was my laziness, but then I had to add more colors here. But anyways, so the point is you have this kind of formulation, right, where you do a binomial pairing, basically between the frequencies of the players, and you multiply them with the payoffs. So these are the payoffs that you would be getting, and this binomial takes care of the coefficients, right? In our case, d is equal to 3 in this case, so you actually get only up till the x squared and such powers, right? So these are the formulas for writing down the payoff entries. So that's for the average fitnesses, but that's fine, right? Because this was all the complication that you needed to go through. Because after that, we still plug it into the same replicator dynamics. As we know, we are still dealing with a single dimension, and that's totally fine. Did anyone try plotting this? Yes, you did. No, the one behind you. Okay, so what you're saying is you did something like this. You start, so you have time, and this is your x, right? And so you're starting here, and then it's going down. Okay. And if you start at 0, it stays, right? Okay. And you have an intuition why? Yep. So either you are starting actually over here, where everyone is blue, so that's 1. And then you see that actually being red is good. So that's why it would decrease over time. But over here, if you start, then if everyone is red, then you're at least doing better because you're not paying the cost. Is that the argument? Right. There is no incentive to switch, right? To being a blue individual in that case. That's true. What was the value of B that you tried? 1 and 5. And what do you see for 5? It drops slowly. Okay, okay, all right, all right. Anyone else? You said you tried similar. Okay, okay, right. Yeah. Okay, so this is one way of looking at it, looking at the time dynamics, right? But since we are looking at the deterministic dynamics, we will try to understand what happens in the long run in this case, because you just run this for long. So you want to look at the phase, at the portrait of it, the way we were trying to look at it before, right? So we have the simplex x 0 to 1, and then we could look at the change, right? So we could see when things are being pushed up, which means that the blue will increase. So if x dot is positive, or if x dot is negative, then things would decrease, right? The blue would decrease over time. And if you do that for different values of b, right? B2, 4, 6. So if you did it for b of 1, right? You said, you see that the line is consistently below the x dot equals 0, right? So that you are always below what you would get, so that you cannot increase in time. So x dot is not positive. And that means over time, you would decrease, right? You would have to run it for infinitely long for the same arguments that Kaylin mentioned earlier. You would never actually go to 0, right? You will go asymptote to 0, but yeah. But the thing is, as you increase b, and that was one of the exercise things, right? You try it out for different values of b. What you do see is that the line moves up, right? At some point it intersects the x dot equals 0, and then it keeps on moving up. And what's happening at that point is that you're creating two internal equilibria of that system, right? This one is going to be an unstable equilibrium, say b equal to 4, because on the right-hand side of that, you see that things are blue. Things are going to be increasing. But on the left-hand side, it's red. So you are going to move towards x equal to 0. So the image looks something like this, right? Okay, I moved this far to the right, but yeah, get the point. Is this part clear? So the thing is, because you are intersecting the x equal to 0, the way you are intersecting it from below or from the top will kind of determine what kind of equilibrium do you find over here, right? Now this will be an unstable equilibrium, whereas this is a stable equilibrium. You can calculate the Jacobians of those if you are interested. And what this tells us is that on this simplex, the same one-dimensional simplex, earlier we saw one fixed point, right? We were seeing the stable or unstable points. In this example, you can see that there are two interior fixed points. You can do some nice bifurcation analysis to show at exactly which value of b the 2 points appear and how do they move. But the point about this is that all it matters is that you look at the payoff entries, right? Because what's happening at the payoff entries is that throughout a change in b, so it doesn't matter if you change b being larger than c, that was one of the conditions, right? If you do that, we do have A2, which is larger than, no, the other way around, right? B2, A1, which is larger than B1, but then A0, which is worse than B0, right? And if you look at the setup of this, you see that the signs of inequalities between the payoff entries have changed twice. And this is something which is very curious, because you can recast this whole argument into what is known as Bernstein polynomial argument. So what you care about then, if you think about it, when we want to calculate the equilibria, right? What did we do when we wanted to calculate equilibria? We tried to do FA equals FP, right? Which meant we did FA minus FP equals 0. That's what we want. Which means at some point we are looking at the differences in the payoffs. And that's why looking at the differences in the payoffs tells us something about how many fixed points can be possible. You also saw that B was larger than 1, so B was larger than C, but you did not always get 2 fixed points, right? You might also get no fixed points. So this is a necessary condition, but not a sufficient condition, the switching of the inequalities. So if you do want to see more than 1 fixed point, you need to check how many inequalities are there in your payoff entry. And this is a really cool paper if you want to follow that up a bit more. Gains from switching, so that's the idea, right? You switch and do you gain? So gains from switching and evolutionary stability in multiplayer matrix games. It's a really good exposition of what Bernstein polynomials brings to the analysis of equilibrium points. So this was just an example, but the takeaway of this is that what's possible in 2 by 2 by 2 games is then you can have 2 additional fixed points, 1 more additional fixed point, right? Besides what we had before. Before we had at most 1, and now we can have 2. So this is the full profile of all possible dynamical outcomes of a three-player game with 2 strategies. Actually, we can just quickly generalize this, and without going into further details, the idea is that for deterministic dynamics, we can actually write down what's the maximum number of internal fixed points, right? For a D-player game, it's just D minus 1, because that's how many times you can switch inequalities. Because we know the payoff matrix that we wrote down was a D minus 1 sized payoff matrix, right? So you can switch inequalities that many times. So this is nice. This is very cool to have a result, but what about the stochastic dynamics? That might be a mess. I'm not going to go through the derivations of that. You can do a bit of math, but you can use basically the same kind of formulation because we are still dealing with 2 strategies, right, at this point. So we are still dealing with transition probabilities up and down. We are still dealing with fixation probabilities of A and B. They look messy, but only when you are dealing with the fitnesses in the end, right? But the formulation stays the same. Before I write them down, please. So the gains from switching is that A2, compare yourself A2 to B2. If I am at B2, if I switch my strategy to A2, will I be gaining anything or not? And that's being told to me by the sign of the difference between the two. But interestingly, for Bernstein polynomials, you can also look at the magnitude between the two, and that determines if you're still below the line or will you at least intersect it at some point. That's the gains from switching. So it's another way of saying that you want to look at the difference in the payoffs. Yeah. So if you do this for multiplayer games, actually what you do see, okay, this is for the 2-player games, which we saw earlier, and these are the quantities and how they look like for multiplayer games. So they do follow through, and as you see, you also get the coefficients correct so you just keep on giving more and more importance as you move closer and closer to the pure strategies, A0 and B0, right? So it follows, again, the same argumentation that you were thinking of. But what we have done basically here is then, because if you remember the interpretation of these quantities, right, the fixation probability larger than neutral and comparison of fixation probability, what do they mean? Well, what we have done is basically we have generalized the 1/3 rule and the concept of risk dominance, right, to these multiplayer games, arbitrary number of players rather. And it was a really cool paper by Sabine Lessard, who actually showed that this extension of the 1/3 rule is actually valid for all the processes which fall under the Kingman's coalescence. So you look at the Moran process, you look at the Wright-Fisher process, you look at anything in between them, you look at any, like, I don't know, ancestry graph, or things like that. If you can fold them under the Kingman's coalescent, the rule actually holds. And that's a really cool thing to see, that it can be actually generalized to multiple stochastic processes, and not just, even though you derive it for the Moran process in a way, because it falls in this same class of stochastic processes, is actually valid then. That was when we increased the number of players, right? But since yesterday, what we have been trying to see is that we try to see how much can we generalize this argument. So what we want to look at is multiple player games with multiple strategies, and hopefully I fixed this cube now, but it looks way more uglier actually now that it is actually symmetric. in my opinion. But anyway, so what we want to look at now is actually 3 by 3 by 3 games, right? So we have 3 strategies and we have 3 players. And what can we actually do for these kind of monsters, right? Well, what we do know is what happens when you increase the number of strategies, right? We saw that for 2 strategies, however complicated the payoff matrix is, because we can construct like these for multiple players. Thankfully, we are still dealing with the same dimension, so things are a bit well behaved. As soon as you increase the number of strategies, you make your payoff matrix large, right? And that means you need to also add dimensions, not to the payoff matrix, but rather to the simplex in which you are looking at the dynamics, right? So we are no longer on this line anymore. Instead, we would be in this triangle for, say, 3 strategies. And the question is, what happens to the maximum number of internal fixed points then? At least talking about the deterministic dynamics, right? Any ideas? All right, yeah. That could be one option. No. Yes. So that is true. So the order of the polynomial does play a role. But the thing is, what's happening now is we had 2 strategies earlier, and that's why we could deal with. So we actually had x1 and x2. We didn't need to track x2, right? We just dealt with x in that case, and the other one was 1 minus x. As you increase the number of strategies, we have x2, x3, and this keeps on going to xn, right? So the simplex, as you can see, that's the argument behind the simplex, right? Why is that simplex 2-dimensional, which is good enough to represent 3 strategies, is because you can actually write down these many differential equations, or at least the variables, in a simplex of s minus 1, right? But the problem is now we are dealing with these many equations as well. And since we are doing that, the nonlinearity, which you get in each one of those equations, needs to be multiplied over. So it's not just an addition or a subtraction, but actually then it becomes a product. And so the thing is, you can actually work through this, like what's the probability of actually, and these things you can calculate analytically actually. So what's the probability that you do get a single equilibrium? For example, in this case, for 2-player games with any number of strategies, we already saw how that would look like, right? 2 to the 1 minus n. Because you just check with the number of strategies, how many of those internal fixed points you might get. But the probability of that one internal stable fixed points, you just need to alternate, right? Because which one is stable, then that will tell you that the next one has to be unstable. If you look at only 2 strategies, that means we were on the line, right? What's the probability that you will get an equilibrium which is stable? Well, that's just half, because anytime you will get a fixed point, it will be either stable or unstable. There is not much to it because we are on the line. But the thing is, you can actually calculate what's in this whole space. Oh, this is an ugly color. Again, it didn't look this ugly on my screen, I have to say. I'll move away from this slide quickly. So the maximum number of internal isolated equilibria actually is then d minus 1 to the n minus 1, because you have d minus 1 in each of those equations, right? And then we have n minus 1 of those, right? So you could, in principle, have d minus 1 to the n minus 1 interior fixed points in those high-dimensional simplexes. So for d equal to 3, n equal to 3, how many fixed points do we expect? 4, and 4 would be the maximum possible, right? So we can show actually this is a hard bound. So for d3, n3, you can get 4 interior fixed points, right? Even for d4, n3, which would give you then 9 interior fixed points, you can construct matrices which will actually give you those interior fixed points. So it is possible to have these complicated dynamics within these kind of games in the limit, right? If we really want to push and look at all possible equilibria, you can actually look for that. In a separate study, we actually calculated the probabilities of seeing these different kinds of equilibria. So if you just draw these games randomly, right, you don't really know which games are happening, and you just draw games at random, and you fill them up. What's the probability that I will actually see in a 4-player game with 3 strategies, 9 equilibria? How often will I see it? And you can calculate these probabilities, not just actually numerically, but also analytically, because you can look at the space of all possible solutions and how many solutions are possible within that space that give you 9 equilibria. But that's much more involved. This is much more fun right now. So I'm just going to show this one. So the cool thing is you can have a maximum number of internal fixed points, d minus 1 to the n minus 1. In principle, you can actually also show the total number of fixed points is d to the n minus 1 over d minus 1. That's the total number of fixed points. So everything that so if you look at the edges, the faces and edges and vertices, and the isolated vertices. The one thing that we have done here is clearly we have excluded cycles and stuff like that. So we are looking only at isolated fixed points. So there is a constraint on what kind of games are amenable, because then they are just easier to analyze in using tools from dynamical systems. As soon as you ask for spirals or circles, cycles, things get a bit problematic. Right. This was my promise to you, that I will come back to why do we look at this and why did we make this connection to population genetics yesterday. There was a really cool comment by Mark Feldman. This was in 2009. Where he said, like, amazingly to this day, our conjecture that the maximum number of equilibria in any n chromosome viability system and for any recombination arrangement is 2 to the n minus 1 has not been proven, although there are no counterexamples. And then Sam Carlin also discussed these things with other people, and they showed that this is possible, but they didn't have the proof for that. The cool thing is if you do these methods from yesterday and actually do the conversion in a different manuscript, then we actually showed that you can write down a proof for that conjecture from game theory point of view. Clearly we overlooked, because actually in 2010, Altenberg had already published using population genetics a proof, and clearly there were some reviewers of this paper who suggested that we read that paper. So that was a good idea. But the thing about this is that you can actually connect, for example, these partnership games to the concepts of population genetics. And you can actually write down a proof in population genetics, which we did not know was important at that time, but you could write that down actually from using game theoretic arguments, and it was much more simpler writing it down from evolutionary games. Because we did not actually use the same terminology, because as soon as you get steeped into the terminology of a particular field, maybe things get narrowed down a bit, but this allowed us to look at it from a different point of view. Not just that, actually, what you can do is that, I think this was a question that Sagar asked yesterday, that you can actually extend this to a polyploid system. Because currently what we have is d equal to 4, right? If you remember yesterday, we did it with a 4-player game. But where does the 4-player game actually come from? Because we also had assumptions on what kind of individuals we were talking about, right? We were talking about diploids. And the thing is, you could actually do it for n alleles with multiploid systems, where your number of players is basically twice the number of the ploidy level. The 2 still comes over here, because even though your system might be polyploid, you need 2 of them to come together. You can also get rid of those assumptions under some other extreme conditions, but right now what we did write down is that you can actually move it to a polyploid system as well. So that was the argument for moving between the fields, and then you can possibly contribute something from one to the other. Yes. Yeah. Yes, yes. So actually, you're precisely right. The thing is, here we try to be a bit more polite about this. It said it would be interesting but challenging to develop the model provided by Altenberg, which was developed using a bit more complex argumentation for a polyploid system and to check the maximum number of equilibria. So we just said that you could do it by this, but if you use this other method, it might be a bit more problematic. So yeah, that was our argument. We didn't state it like that, but hopefully not. No, but there is, I mean, cross-fostering, yeah, of ideas then between the fields, I mean, of course. Yeah. Precisely. I agree. Yeah, and also, but one of the crucial things is, do the interpretations carry over? Because once you change the coordinate system, can you change it back to make the mean? Does the meaning still remain the same? And I think that is something that one needs to be careful of here. In this case, we try to be, but yeah, but otherwise, yeah, you can map basically one problem to the other and then solve it there, and then map it back, and that's the second part which is important, and mapping it back, the solution. Yeah, yeah. Yeah. Yes, at that point we did, but we made assumptions at that point to when we carried it over. My point here is that once we did the analysis and we got the results, were we able to carry them back to population genetics? That's where I'm a bit worried, because usually then what people do is, oh, this is a great problem, I'll convert it to something that I know of, and then we just stay there. Yeah. Uh, yes. Clearly, yeah. Before you translate it back, then. Yeah, yeah. Yeah, because at the end, then once we knew that we had made the assumptions, what popped out of it was again just this a, it was small a, right? A, small a, right? This is the thing that popped out after, in the simplest possible case, where all the assumptions were in there, which is like said, like, oh, we don't need to do the two-player, don't need to do the four-player, we could do the two-player thing, and that was because this has a very good meaning in population genetics, and then you could translate it back, because then you could see that, oh, I see the genotypes now, I see the genotypes, I see their fitness, and this was useful. But in between, it was a bit murky, and you have to justify the steps. Yeah. I would refer you to the Altenberg paper. I found it a bit hard, but that might be biased because of my background. It might be biased. Yeah. I, but yeah, but I think if you look at the dynamics, right? So I would not even care that I need to show that in the evolutionary game theoretic framework or the population genetic framework. If I can write down the selection equation, which we saw yesterday, which is exactly the same, right? And just explain what that selection equation means. Because if I'm giving a class for the population genetics, I would use the terminology for that and then use that, right? Terminology. But in the end, you will actually be using the same mathematical framework. And that's at that point. So for example, for talking about the selection equation, I would use that. Yeah. That's really fun discussion. I would love to discuss this, because one of my interests is about the plurality of methods that one can use actually for tackling problems. And one, it's my opinion, okay, this is getting philosophical, but I feel like one should not get fixated by one particular set of methods if we want to tackle a broader set of problems. If not, that's fine. It's totally okay. It's totally justified. Yeah. We will talk about that tomorrow, actually. Yeah. So that's connecting it to ecology, and we will talk about the connections to ecology tomorrow. Yeah. All right, so we are here. I need to stop. Okay, this is fast. So we talked about the deterministic and stochastic properties in multiplayer games, and I hope that part is fine. Now we are going to be talking about the time, right? So the time issues can be different about calculation of fixation time and all. So I decided I would jump directly to a question which is, or at least a property which is quite curious. And this is a system which you recognize, the one on top. You start with all B population, you want to end up in an all A population. You've started with a single A individual, right? And the dynamics on this is again given by your transition probabilities up, transition probabilities down. Now let's think of an even simpler process, right? As compared to the games. Forget about the games right now. It's a simpler moron process in which you just pick an A individual for birth and B for death. That's fine, that's possible. That's how you will increase the number of A individuals. Or you could choose a B individual, the B individual mutates, and it dies, right? So it mutates to an A, and then it dies. So that means you have also increased the number of A individuals by 1 in that case, right, with the mutations. The transition probability to reduce the number of A individuals is basically just you choose a B individual who does not mutate, but an A individual dies. So now this is an asymmetric process, right? Because the A individuals are actually not mutating. So there is a constant push towards going towards the all A, right? So it has nothing to do with fitnesses right now. The mutation process is just pushing you towards A. Is this okay? Yeah? I mean, it's just set up like that. So, I mean, what can we do? So it's done, but it's fine, right? It's understandable. So the mutations are going to push you towards A, and the strength of the bias, it keeps on decreasing, but it's still positive. It's pushing. Yeah? It keeps on decreasing because at some point the number of B individuals will be less, right? So the effect will be less. You would, but then it would not be a directed process. I really want to have a directed process in this case. Then you allow for back mutations, then yes, things slow down a bit. Yeah. Okay, then we are talking even more about asymmetric mutation rates, then yes. Asymmetric, yes, that would work. Yeah. Yeah. Okay, but this is the setup so far, and we are interested in the conditional fixation time, and conditional means like given that you reach fixation, how long does it take? Okay, that's all it says. Given that you reach fixation, how long will it take? So how long will it take? So if there is a neutral dynamics saying that there was no bias, right? If there was no bias towards moving towards A, if it was just equal, like moving up or moving down, and say that's the neutral fixation time, what would this process give us? What would happen to the fixation time in that process? Right? You have the fixation time for a single individual of population size n. Right? This is the neutral fixation time, let's just say. And as I do have these mutation rates, what happens if I'm actually increasing the bias, right? Increasing the mutation rate towards A. It should be decreasing, right? I mean, it should just go down, right? Start with no mutations, which is a neutral process, and then you increase the bias, you go to the right. And then you see actually something like this, right? You see a one-humped process, actually. So for very weak mutation rates, in this case, you see that the fixation probability, if the fixation time, this conditional fixation time, it takes longer to fix in A than it would by neutrality, as compared to neutrality. And there is an intuitive reason for that, because when you look at again, the formula for the conditional fixation time, it has these components in which you have the fixation probability, and independently you have the transition probabilities, which are being also shown. And what happens is that your fixation probability definitely increases, right? Because you're moving your bias towards there, and your fixation probability says that, okay, there is a very high likelihood I would fix. But your transition probabilities, which are appearing in two places, they're actually decreasing because your T plus, right? The probability of moving to the right, it's appearing in the denominator. And that keeps on pushing your process down. So it's a tug of war between these two processes. Your fixation probability is increasing, but the transition probabilities are decreasing. Well, the ratio of them and the 1 over T plus. And you can actually see this also in a slightly different process where you actually do it with selection intensity. So you do have these hump cases all the time for fixation probabilities, fixation times, again, this is normalized. for 2, 4, 8, this is the number of players that you have. And you can see as you increase the number of players in your game, this hump shape actually gets even more exacerbated. So what it does is basically this idea of stochastic slowdown, where you have a process which is pushing you towards fixation, but you move there, but you don't move there faster than what you would do by neutrality. And the reason for that is then you have to look at sojourn times. So the time you spend in each state. So at the beginning, you don't spend too much time in these states, right? Because your probabilities of moving to the right are quite high because they're driven by the B population. But as the B population drops when you reach closer and closer to the A, the pressure to move to the right actually reduces so much that actually you spend a lot of time in those states as compared to by neutrality, what you would spend by neutrality. So the overall time that it takes to reach full A population actually then becomes larger. It only happens for the small window of mutation rates and selection intensities, but once they're large enough, then you do see this behavior, right? So this is what we termed as stochastic slowdown, and we thought like, oh, this is just a curious case, that's great. You can use some methods from physics and then understand this. Why would that be so interesting, right? Some of our colleagues actually decided, oh, this is interesting. We actually can make use of this by looking at at mutations which are weakly deleterious, for example, in the population, and why do they last so long in the population much larger than what you would expect a neutral mutation to last? Or why do weakly selected mutations take much longer to fix in the population? And you can use the analysis from actually population genetic data in humans, in this case, actually, to look at the fixation times of weakly selected mutations and the persistence of slightly deleterious mutations. If the mutations are slightly deleterious, you would expect them to be removed from the population, but they are actually sticking around for a much larger amount of time than they would if they were just neutral, actually. It's kind of curious result, but they could argue that what we saw actually is transferable in that case. So you do see that there is a bit more mixture between the disciplines in that case. And now we come to the last part, which is like what happens in the long run. So since we did talk about these mutations in the end, let's take that to the extreme, right? Let's talk about mutations in general. And this would be the space to talk about. So usually we are very happy to do some approximations. Usually you do an approximation for weak selection, so we are doing somewhere here. Or then you can make statements for any mutation rate, or you do the other way around. You say that the mutation rates are very low, and then you can do some stuff for any intensity of selection and things like that. Because what the problem is that because of this mutation probability, so if you do have a simplex, for example, like this, what mutations do is basically they constrain the space, right? They constrain the space in which you can actually see the strategies. Because if you keep on flipping all the time between the strategies, no matter what the selective advantage, I mean, okay, you can move a little bit, but the argument is if you constantly mutate to different types, you basically are close to a well-mixed, to an equilibrium state which is well represented by all strategies, right? This space is the thing that keeps on getting squeezed and squeezed as you increase the mutation probability. And then we can ask some questions, okay, if this is the case over here, what happens if we actually do something about the selection intensity, and can we understand this space better? Make some good approximation on selection intensities. So here what we have done is like you can look at the long-term abundance. So X, K, delta, how do I read that? The way I would read that is it is the average frequency of a strategy in the mutation selection equilibrium. Okay. So what the strategy profile, what the strategy frequency looks like in the long run when it has been subject to mutation and selection. But we will make some approximations on the way, because the idea is if you have a lot of mutations, as I just said, it will be equally represented just like any other strategy, right? And that means 1 over n. If there are n strategies, the frequency would be just 1 over n. But then you do get some corrections because of mutation and selection, right? And those corrections are captured in this term over here. So this 1 over n plus something, and again, we do the same trick as before. We just ask, is this something larger than 1 over n, right? So if this is larger than 1 over n, if this something, whatever is after this addition term, if that is positive, right? And that something is basically this object over here, which is not really nice, actually. So I'm trying to gloss over a lot of these things, a lot of the details over here, but just to show you what the main object looks like. It does have the selection intensity, delta. It does have the mutation rate, mu. It does have the population size over here, but what you can actually abstract out is this LK, MK, and HK. And the nice thing about this is, the nice thing about packaging your variables in such a way is that this LK, MK, and HK, they are basically functions consisting only of the number of strategies and your payoff entries, right? So we have separated out, again, the whole process of mutation and selection and the game itself. So the way it is written down, that you can study the game by itself and the process separately, right? That's how the function looks like, at least. You can write down that for an arbitrary D, and it's just that LK, MK, HK appear for D equal to 3. For an arbitrary D, there will be D of these terms. LK, you can write MK1, MK2, MK3, all the way to, I guess, HK, D minus 1. So there will be D of those terms. But the thing is, all of them will consist only of the number of players and the payoff entries. And as soon as you have that, you can do something nice with it. You can say that, okay, I'm putting all my game details in these containers, and I have the process details outside. Or I could put my process details in a container, and I have my game details outside. Because now it's just a matter of reshuffling how you write these things down. If you do that, you can actually do something much more powerful. Now this container can contain not just the stochastic processes that we have been discussing about. You can put in other things like population structure, update rules, like what different kinds of copying mechanisms which you might think in the population. You can put a lot of other mechanisms of the process in this container and just put the game details outside. And then it looks something like this, right? Where you have the sigma, which is the game container, but all it has on the outside is just the payoff entries. So we have recast this much complicated looking object into a slightly simpler looking object, and with that, what one can do is you can actually write down what the average abundance would look like. So for a two strategy case, all we have to say is, when is this larger than 1 over 2, right? 1 over n, in this case, n equal to 2. And you can write this down for weak selection, but for any mutation rate, how it looks like. And if this inequality is satisfied, we will know that the average abundance is actually larger than neutrality. The other end, we had already seen it, because on the other end, we looked at the fixation probabilities. When you had no mutation rate, then all that matters is, do you fix or not? And we already know information from over here. So within this whole space, we can actually expand on both weak selection and any mutation rate, or weak mutation and any selection intensity, and have some good inequalities to test, which tell us when is a strategy doing better than the other. And it's valid for any number of players. So this was the last part, and I have 7 minutes. Not sure I think I could, yeah. You might be very tired with this, yes, please. Can you speak a bit loudly, please? Yeah, I think it will work if you keep on talking. Yeah. Yeah. Yeah, it's a bit tricky. I think I don't remember if there is some method which is beyond what I will say now, but if there is, I think maybe Sylvia knows. But before that, I'll give it a try. So what you usually do in that case with multiple strategies is you do a pairwise comparison between all possible pairs. And then you see what happens if will A invade B, will A invade C, will A invade D, and then you do that all for B invading A, B invading B, B invading C, B invading T, and all the pairwise combinations, and then you calculate the long-term stationary distribution from that. And if you calculate the long-term stationary distribution, that will tell you, because then it's basically a transition matrix, a stochastic transition matrix, right? If you write down fixation probabilities of that. And you then take the left eigenvector of it, the leading eigenvalue, which is 1, and then that will give you the long-term stationary distribution. But that's still for multiple strategies and for multiple players. But if there is another way, because this makes the approximation of still looking at pairwise first, so I don't know if there is a better way of doing it still, but I don't. No, that's what I mean. So you just do it for pairwise, and then you do it. But I don't know for more than that. That's what I'm saying. Yeah, yeah. No, I haven't found one. Well, the thing is, it works very well. You can compare it with simulation results. It works very well because you can do some, because again, it's valid for weak selection intensities. I think you can extend it to larger selection intensities, but I don't know. There are some limitations on that. Yeah. Yeah. But it works usually totally fine. Yeah. The assumption is of also weak mutation, because by the time these fixations happen, you need to make sure no other mutations arise. So there are these constraints on mutation rate, selection intensities and stuff. Then it works fine. All right, this is what we actually went through, the first part. And as I said, if time permits, I'll really try to see if I can use 5 minutes for this. But if not, I will be fast, I think. Yeah. So the thing is, I wanted to talk about something which is like much more, a bit more, hands-on, not really that much, but still a bit more hands-on, because we were discussing all these methodologies, and the idea was like, do we implement some of these at some point or not? And how, like, is it just for curiosity because you can do it? Or where do we actually apply it? So this is just for the deterministic part, at least, because we are not going to use the stochastic one. Those we might see something tomorrow. But for the deterministic one, I decided to focus on mutualism and using evolutionary multiplayer games in it. And usually when you think of mutualism, the first question that comes into mind is like, how do they evolve and what keeps them from breaking down? And then the typical frameworks which people have been using are public goods games or prisoner's dilemma, right, in this case. And then the solutions typically rest on the concepts of reciprocal altruism, partner choice, because if you just choose your partners properly, or it's a byproduct mutualism because you are actually playing a different game and this mutualism just happens as a byproduct of that, or it's a pseudo-reciprocity strategy. The thing is, we are not going to ask this question, we are going to ask a slightly different question. The question that I want to ask is, given that there is mutualism, how are the benefits of those mutualisms split in an evolution, like via an evolutionary process, right? So that's a slightly different question. So the benefits are there. Now, how do we share them? So it's something similar to actually what we heard today morning. So we do want to generate the benefits are there, but now the point is like, how do we share them? Like who takes how much, right? So there is no zero, so there is no strategy for no contribution over here, but the game that we will play is basically something like this. You can be generous or you can be selfish. You want to keep it for yourself, but the thing is, that's also what the other species can do, right? And as I said here, it's a different species, so actually this is not the right framework, right, to write it down. So the right framework would be, this is what species 1 has, the strategy G1 and S1, and this is what species 2 has, strategy G2 and S2. And since they are two different species, actually you should have two separate matrices for them, right? So these are two different populations, species 1 and species 2. Species 1 has two types, being generous or being selfish, and species 2 has two types, to be generous or selfish, right? And both of them have a certain structure, right, for the game. And so this structure you might recognize already from the morning. The reason because you have two different populations, now you do need to write down two different replicator dynamics, right? You have replicator dynamics happening in population 1, which is X times FG1, which will be a function of Y, right? Because this species is interacting with the other species. So now I depend on the frequencies of those types in the other species, and that's Y. And the average fitness then depends on the frequencies also of what's happening in my population and with the other population, because that's where the fitness is coming from. The same thing for the second population. So the Y dynamics depends on how the X looks like. That's where its fitness comes from. And the average fitness it comes from then both X and Y. Is this okay? So there is dependence between the two populations, right, through their interactions then. This is what initially the game looks like, and what, again, you have seen such kind of figures before. So what's plotted on the x-axis is just the frequency of selfish individuals in species 2, and on the y-axis is the frequency of selfish individuals in species 1. And then you see that you go to these equilibria in which one of the species can be fully selfish and it forces the other one to be generous. And it's equally split, right? Okay, I asked them to put the timer 5 minutes earlier, and that was the plan. So actually it's 1 hour 20 minutes now, and I think they tried to put it for 25. Is that right? Exactly, so I have 5 more minutes, exactly. Yeah, this was for my benefit and not yours, so sorry. But the thing is, what happens if you actually let them evolve at different rates? Because they are two different species, usually these two species having similar rates of evolution would be quite a strong assumption, right? So if you let them have different rates of evolution, you see something interesting. In this case, species 1 is evolving slower, right? Species 1 was given over here. And then it evolves to the top left corner where it can be selfish and it forces the other one to be generous. Here, the species 2 is evolving slower, and all the blue arrows, they lead to it becoming selfish and forcing the other one to evolve to be generous. And what you see is that now the basins of attraction of those equilibrium points have shifted. The species which evolve slower gets more points from the interior of this two-dimensional phase portrait to reach an equilibrium which is favorable to itself. The slower evolving species can be selfish, and it forces the other one to be generous. And this was termed as the Red King effect, because in the, as you know from in ecological and the arms race and ecological terms, so you force the other individual, your co-species basically to evolve faster and faster because you want to evade the predator-prey kind of dynamics. In this case, actually, in mutualism, if you evolve slower, you force your partner to adapt to you and to your own terms, and you can basically dictate the terms of engagement then. So that's the argument which Bergstrom and Lachman pushed in 2003. We decided, okay, let's formalize this a bit more clearly. Species 1, 2 types. Species 2, 2 types, right? They are both taking part in a game. The game can look very different from each species' point of view, right? I mean, I'm having a mutualistic relationship with a certain different species. Maybe they think of that interaction much more than I do, right? It could be different. So they do take part in these games, but in principle, you have this interdependence between the populations, and you have the different growth rates. The specific game that they looked at was the snowdrift game, a version of the snowdrift game, right, with B larger than C, and this is how the fitnesses look like then. So fitness of one of the types in species 1 depends on the Y and 1 minus Y, so that comes from the other species. Right? This is a framework that you might have seen before. What we wanted to do was, okay, let's understand what happens if you do add more interacting partners, right? And this is something that people have studied before experimentally. For example, this is the lycidid larvae and ants, and we are going to be hearing more about ants later, so this is pretty cool segue into that. So the idea is that you have a total number of ants which are grooming these larvae, and the larvae provide them this very nice droplets of honeydew, which they can use for their nutrition. And the amount of honeydew which is produced increases according to the total number of ants, and it's not just the total number of ants, it's ants per larvae actually is increasing, right? So they are being groomed better. So each caterpillar, each larva is being groomed by multiple ants at the same time. So if you want to track down the interactions between these, we could actually move to a multiplayer game, right? And that's what we tried to do now. Instead of this particular game, you can say that, okay, species 1 plays a 3-player game and species 2 plays a 3-player game. And then things become a bit more complicated, right? The matrix doesn't look just symmetric like that. Before there appears this column which we need to understand what's happening there. But the thing is, you can write it down because you can write down an extended version of a snowdrift game for multiple players. And then what appears is that there appears this M. So in the snowdrift game, the idea is like you want to contribute, right? If no one else is contributing, then you want to contribute. But at what time do you start doing that, right? How many other cooperators do you need to have so that you actually start doing that? And this is what this M says. M gives you the threshold, right? At what point does it make sense to actually start contributing? You can do the same analysis that we did over here before. You write down the payoffs for the multiplayer game, and similarly for the second species. So right now I just showed it for the one species, but you have to do it also for the second species. Right? If you do that, you see something like this. This is for D equal to 2, so 2-player games, and we saw this before. The phase portrait, it's equally split, right? The phase space is equally split. For Rx, which is evolving much smaller than Ry, so in this case, everything evolves to this top left, because species 1 can actually be very selfish, and you can force the other species to be more generous. Yeah? I will come to that. I'll come to that. I'll just go through this first, and I will come to that. Right. For multiplayer games, the Red King effect is actually reversed. So if you see a lot of points over here, they're actually going over to the generous vertex of species 1. And although species 1 is evolving slower, right, it forces most of the interior points to actually lead to the point where actually it is being generous, right? So actually you don't see the multiplayer effect, the Red King effect anymore if you allow for multiple players in this case. So you can actually change the size of the basins of attraction of those two fixed points. So you can offset the costs that you were getting by evolving slower by changing the number of players that are involved in that game, right? And adding multiplayer game actually is pretty cool because that allows us to add bits of realism to it, right? Things like, for example, you might not have just both playing 3-player game. One could play a 2, one could play a 3-player game. So you could have things like asymmetric number of players where you again see movement in the size of the basins of attraction, or you could also see asymmetric thresholds, right? As I said, like you need some amount of individuals to actually start generating the public good. And if you don't, you actually completely destabilize the system. So if you have different number of thresholds, you can actually even get rid of the equilibria on the side, and you can start getting cycles inside the system. So you can maintain the selfish and generous types in both the species, even though you might think that, okay, this is just a snowdrift game and mutualism, why don't the selfish or generous types take over? Well, actually you can get cycles throughout. So this is just to show that actually including these multiplayer games within a mutualistic framework can actually change the kind of qualitative outcomes that you might expect and not just the quantitative, right? So the idea behind this was, okay, the asymmetry in the number of players, thresholds, and other game parameters actually may be more under control, right, of that species. I mean, they can't just willy-nilly change the evolutionary rate, which was causing a cost. So maybe to offset the costs that you have because you are evolving faster, you might just invest with more or less number of players in that interaction. And interesting questions about mutualism benefits can be maintained where the exploited option is also preferred than by the type that is being exploited, right? So this is very close to if you are thinking of these extortion strategies, right? It's very close to that idea. Well, here we consider only interspecies dynamics and not the intraspecies, so you could also have intraspecies dynamics, but we studied that separately. So that's basically all that I wanted to do. I made sure that there is no way I could cover eco-evolutionary dynamics now in this case, because that was ambitious anyways. But this was actually my aim. That should have been fine. So I am happy to have met that. And that's pretty much it. And if you have any questions, if we have time, I would be happy to take them. Yeah, that was. So the intuition behind that is that because you're evolving much slowly, the response that you would give to being exploited doesn't really come out that quickly. That means the other species doesn't gain anything instantaneously. So you actually force the other species to adapt to your timescales to get any feedback, to get any product of this mutualistic interaction. Because then you would just not give any product until the time comes. So the time scales actually dictate which one is a much more powerful player in this case. Sorry? Yeah, that's when the case was when Rx is equal to Ry, right? So if that was when it was close enough. And there you see that then it just split equally. And then it depends on the game parameters, of course, but for the usual game, it's just split equally, yeah, the basins of attraction. Yeah, so the last paper that I mentioned, it has that. Yeah, I can show it to you again. Yeah, sure, sure. What's happening here? This one. Those were the isoclines for the fitnesses actually. So the way you solve it, right, is the way you do it is you have so you have three strategies. So you want to solve FA equals FB, FA equals FC, and well, FB equals FC. So it's basically plotting all three of them, and then you see the isoclines how they look like. Where they intersect, you start getting those fixed points. Yeah, that's just how geometrically the isoclines look like.
Yeah, this was so interesting, but the last bit went fast. I was wondering when you're doing, of course, I mean, when you were doing the multiplayer games in this case, how you were thinking about like when you have two players from one side, them splitting the benefits of the mutualism. Is it that there's some proportion that one species is getting and then the multiple players in the other species have to split what they get, or yeah, how did that work?
That's a good question. So the game basically looks something like this for both species in a way, because then you just change the labels. But the way it looks like is like, okay, so this one is one individual, like on an average, one individual from species one in this case, who's being generous, and then they interact with these possible combinations. Right? And once they do that, you can get the entries of the payoff matrix which come from this interaction. So this is what each one of them gets on an average. So if when they go play against the other species, they would get each one according to this. So yeah, this is what you could interpret as what each one of them gets.
Okay.
Yeah, on an average.
I can't see it, but so there isn't an interpretation that, like if we were talking about the lycanids, it's not an interpretation where the two ants would take that and then somehow split it between them.
No. Yes. Good. Yeah. You could do that because you could do that like on the size of the group, and then you could split the benefits on the size of the group. So for example, right now you do have this B, for example, B minus C over K. And this K kind of tells you how many other cooperators are there within the group. But since currently we only look at interspecies dynamics, that's why it doesn't matter how does your own group look like. That's what we have done in this other paper, what I was mentioning, because at that point, then you all have to include not just K, which comes from the species 2, but then you also have to look like what my own group looks like, and then how do I split it. So that's something that we looked at in the other one. So there you have to look at intraspecies interactions as well. Exactly. That's when this FG1 and FG2 would be basically X and X comma Y. Isn't there talk? Talk? No, there's talk first. Yeah, yeah.